Hello everyone, welcome back to the mechanical vibrations tutorial. Today we are going to discuss an interesting case of two degree of freedom systems, which is the semi-definite systems. So let's begin. So what is a semi-definite system? So a semi-definite system, which is also known as a sort of unrestrained or degenerate system, is the case that the system has a little bit more of freedom compared to regular 2 degree of freedom systems. So as you remember before, in regular 2 degree of freedom systems, we had, say for example, one spring one side or the other side. But in this case, as you see in this basically representation, we have only one spring between the two masses. And the other cases that I can show you is, say for example, we have one disc which is connected through a shaft to another disc, and these shafts have each one has J for example J1 and J2, the two moments with respect to the center, and this shaft the central shaft. So these two discs are the two basically mass components, and the shaft has a sort of torsional stiffness, and this is also another case of a semi-definite system. So basically a semi-definite system, like I said, is also known as unrestrained or degenerate system, right? So these are other names for a semi-definite system. So let's basically dig into the problem and try to derive the equation of motion and basically set it into the matrix representation and find the natural frequencies and see why this is a very interesting case and why it is different from regular examples that we have before. So to find the equation of motion, same as other cases we can give a, say for example, x1 this way, then we have a force in between which is k, x2 minus x1, and what is basically x2 is here, so we have m1 and m2, and then we can basically use the Newton's law for each mass. We have m1 x double dot 1 equal to minus k x2 minus x1, or actually they are in the same direction, the force we have to use positive here, doesn't matter, you can basically find the right signs. And then we have m2 x double dot 2 equal to minus k x2 minus x1. Why? Because the force is in the opposite direction of x2, right? If we put everything in the left hand side and simplify the equation, we can basically set it as m1 x double dot 1 plus k x1 minus k x2 equal to 0. So this is k, and m2 x double dot 2 plus k x2 minus k x1, or you can write x1 first, doesn't matter, equal to 0. And then if we set it into the matrix, we have m1 0 0 m2 x1 double dot x2 double dot plus k minus k, and it's a very symmetrical matrix, k times x1 and x2 equal to 0. Then we can, as you remember, set xj equal to x cos omega t plus phi j, right, where j is 1 and 2. So x double dot j is equal to minus omega square xj cos omega t plus phi j, and then we plug these two terms into the above equation and simplify or factor out cos omega t phi j, because it is repeated in all components, to set the characteristic equation, or basically the matrix of coefficients, and finding the determinant. These are all the steps that we took before, so I don't want to go into the details. I'm sure that you remember based on the previous cases. So what we have is we have minus m1 omega squared plus k minus k m2 omega squared plus k times x1 and x2. These are amplitudes equal to 0. So we set the determinant of this matrix equal to 0, and if we do so, what we get from the determinant, this is the interesting part. So determinant is this term times this one minus this multiplication. You know how to find the determinant for a 2x2 matrix. So if we find the characteristic equation or the determinant of the coefficients, we reach to an equation to something like that. If we factor out and simplify, we get omega squared times m1 m2 omega squared minus k m1 plus m2 equal to 0. So we can simplify to this equation, and the interesting part is this equation gives us two frequencies. One of them is 0, right? Because it's a multiplication of two terms. To be equal to 0, at least one of them is 0, right? To find the roots, we don't have to go through the delta formula because it's a simpler or simplified version of a quadratic equation. And omega 2 is equal to k m1 plus m2 divided by m1 m2. So here's the difference between the semi-definite system, like 2 degree of freedom system, and a regular system or regular 2 degree of freedom system. One of the frequencies, or the first natural frequency, or the frequency of the first mode shape is equal to 0, right? It's very interesting. It's different. Previously we had two non-zero expressions for the frequencies, while for basically this case we have 1 0. So let's see what happens later. So based on what we find here, I just defined this problem, which is asking for the mode shapes and time responses of a semi-definite system below. Like I said, a semi-definite system could be different representation, different systems, like two discs and a shaft example and stuff like that, in gears and in many other cases like axles. So it's not like limited to this case. Sometimes we have two discs, rotary discs, that are connected through a spring, and then there is a rotation. Again, the vibration in x direction could be represented as a semi-definite system. So you can imagine how important and interesting this case is. So in order to find basically the mode shapes and time response, let's basically follow the rules and the methods that we shown before. So we found omega 1 and omega 2, same as the expressions we had before. So what we have here, basically we can basically say, okay, we have minus m1 omega 1 squared plus k for the first mode, right? Minus k minus omega 2 squared plus k times x1, and instead of basically, because it's the first mode, we can say x11 and r1 x11, right? We are looking into the first mode shape. So this is equal to 0, right? And then we can either use the above or the below equation to basically find r1. So let's use like the top one. So we have minus m1 omega 1 squared plus k times x11 minus k, and this is x21, right? So k r1 x11 equal to 0. I'm sure you remember how we define the amplitude ratios for each mode shape, right? So r1 is equal to basically m minus m1 omega 1 squared plus k divided by k, right? So same thing, and this is actually equal to x1 or x2 1 divided by x1 1, right? Like I said, I suppose you know this stuff because we did that before. So just to recall, for the first mode, so mode 1, which belongs to omega 1, we have x1, which is equal to x1 1 and x2 1, and we know that x2 1 is equal to r1 x1 1, right? These are what we had before, right? So we found r1 equal to minus m1 omega 1 squared plus k divided by k. With the same procedure, we could find r2, right? And what is r2? I'll show that. So for r2, we have minus m1 omega 2 squared plus k divided by k, right? Same thing applied here. We just use omega 2, right? So for this is actually, if I separate top and bottom, this is for mode 2, where mode 2 belongs to omega 2, and we have x2 equal to x1 2 and x2 2, which is equal to x1 2 r2 x2 2. Everything basically same as before, and this is actually x1, so we have x1 2, right? Okay, this is basically the same as before. The only difference is the expression here for r1 and r2 are different here and there. So let's plug in what we found for omega 1 and omega 2 here and see what happens. So if we basically remember, we found omega 1 equal to 0 for this case, and omega 2 equal to the square root of k m1 plus m2 divided by m1 m2, right? For r1, we got minus m1 omega 1 squared plus k divided by k, where we know omega 1 equal to 0, so this is 0 and gives us 1. Interesting, right? So the first amplitude ratio or the amplitude ratio for the first mode is 1, and for r2 we just have to plug in, this is omega 2 squared, so omega 2 squared plus k divided by k. So let me double check if, yeah, this is actually omega 2, and then if we plug in this omega here, so this omega we squared and we plug it in there, we can simply find it as minus m1 divided by m2. You can basically double check. So you see it's the ratio of the two masses, which is very interesting. So why don't we do that? Like, let me do this to ensure that I'm calculating correctly. So what we have here is equal to minus, I'm using a different color, we have minus m1 times k m1 plus m2 divided by m1 plus m2, because it's square roots, plus k divided by k. So I'm sure if you simplify these two expressions, this is actually m1 times m2. So if we simplify, we can simplify a k from here. So this is 1, this is 1, and this is gonna be 1. Like, we factor out and simplify, and we can get minus m1 plus or divided by m2, and then basically plus, or this is actually minus 1 plus 1, like the one here. So we get minus m1 divided by M2, right? This is very interesting because we found it as you can see here. Okay, so if you want to double check, just try to expand the the brackets and calculate. So now we found the two mode shapes. Basically we found x1 equal to r1, which is 1. So this is basically x11 1 times x11, right? So this is r1 equals to, we can factor out x11 times 1 1, right? So x2 or basically the mode shape goes up. We have x2 equal to x1 to r2, which is minus m1 m2 x1 2, right? Again, we can factor out x1 2 and we get 1 minus m1 over m2, right? So finally we need to combine the two mode shapes to find the response of the system. So we have basically, as you remember, x1 is equal to this matrix x11 1 1 cos omega 1 t plus phi 1, right? And x2 is the amplitude, which is x2, or it's actually, let me write again, and why don't I use a different color? So the time response for the second mode is x2, so this is t, remember. The second mode shape is x1 2, so this is 1, but this one is 2. 1 minus m1 m2 cos omega 2t plus phi 1, right? Sorry, phi 2. And then we can expand and add them together to find the final response of the system. So you remember, and I repeated that several times before, that the final response of the system is the summation of its mode shapes, right? But before we move on, let's simplify a little bit. So again, x1t, and this is like a vector, is equal to x11, right? And x21, and these are all, now it's just a function of time, is equal to, now we can use the expression we had before, x1 1 1 1, and we have cos omega 1t, which is 0, so phi 1. That's it, right? You see, it's very interesting. It's actually a constant, or basically there is no time applied here. So what's next? We get x2t, the second mode is x1 2, x2 2, and these are basically little letters, which means it's the time basically function, which is equal to, as you noticed, x1 2 1 minus m1 over m2 cos omega 2t plus phi 2, because omega 2 is not 0, right? Omega 2. So eventually we can combine them for each system, or for each mass. So for each mass we have the summation. So x1t, the final response of the first mass, is the summation of x11 plus x12, right? And to better clarify it, I'm gonna use a t here. Basically this is what we place here, plus x12 t, and x 2t is x 2 1, the first mode shape, plus x 2 2t. We can find them in here, right? So if we do so, we're gonna get x1 of t equal to, well, you can simply imagine x1 1, or you can use a constant cos phi 1, right, plus x1 2, right, cos omega 2t plus phi 2, and x2 of t is equal to same thing, x1 1 cos phi 1, same thing repeated, plus, or let's say minus here because we know that, so we have minus m1 m2 x1 2 cos omega 2t plus phi 2, right? So now what are the unknowns? So we have x1 1, we have x1 2, phi 1, and phi 2, right? So as you see, the first component or the first term of the responses for both cases is a constant, which is not a function of time. However, the other one has t appearing in the system. Why? Because in the first frequency we found it as 0. So now we just need 4 basically initial conditions to find these 4 unknowns. As before, we need, say for example, x1 at 0, x2 at 0, x dot 1 at 0, and x2 dot at 0. So if we know this, we can basically apply these initial conditions into the above equation, same as before, and find the 4 unknowns and the time response of the system, right? We can try for some numerical values, just like, say for example, we can select k, I don't know, m1 equal to 1, m2 equal to 2, and then you have k, well, like for k equal to 200 Newton per meter, and then the initial conditions I can give you is x1 0 equal to 0.1, and the other initial conditions are like x dot 1 at 0 equal to x 2 at 0 equal to x dot 2 at 0, all equal to 0. So there is only one initial value which is not 0, which means that we, say for example, pull the first mass for 0.1 meter to the right hand side, or to the toward the direction of x1, right? So you can just give it a try. I want to give you this like a practice problem or something. We can try to find basically the unknowns of the problem using this initial condition. So just as a practice problem, you can try it on. So before we end up this session, I just want to explain a little bit what it means that we have a frequency of 0 here for this case. So we got omega 1 equal to 0, omega 2 equal to non-zero value. So for this case, if we imagine the system like just as a hypothesis, only basically moves or vibrates, or let's say move not vibrates, using the first mode, the whole system actually moves together like a rigid mass, like everything goes one way together, and there is no relative motion in between. So this is how the first mode applies, or how the first mode works, while the second mode is where we also have a combination or a relative motion in between, like they go opposite, or one goes more than the other, right? Or the system goes in the opposite way. So there is a sort of, a relative motion in between when we have the second mode. However, in overall, the system response is the summation of them, which means that the system may move together while there is a relative motion in between. Say, for example, the two masses going to one way, and at the same time they have a different displacement with respect to each other. So this is how we can imagine a semi-definite system motion, and why we have a natural frequency of 0, right? For the natural frequency of 0, it's more like moving together like a rigid system, right? There is no sort of vibration. So I hope you enjoyed today's example, which is very interesting, and stay tuned for the next videos. Thank you.